size a three-phase service panel in amps, firstly calculate the net calculated load, or NCL. This involves determining the connected load in volt-amps, often abbreviated as VA. Apply appropriate demand factors and diversity factors to account for intermittent usage. Demand factors reduce the calculated load based on the likelihood that all connected loads will not operate simultaneously at the maximum rating. Diversity factors account for the varying usage patterns of different loads over time. Secondly, convert the NCL to amperage. The formula for single-phase circuits is amps equals NCL divided by voltage times power factor. For three-phase circuits, adjust the formula as follows: amps equals NCL divided by the quantity of the square root of 3, which is approximately 1.73, times voltage times power factor. Thirdly, adjust for a high leg if applicable. If there is a high leg, increase the amperage calculated in step 2. Note that sometimes a three-phase system does not have a high leg, also known as a wild leg or a stinger leg. If there is no high leg, skip the third step. To compensate for the higher voltage on the high leg, the adjusted formula for three-phase with a high leg is amps equals NCL divided by the quantity 1.73 times voltage times power factor. Let's consider an example of sizing a three-phase service panel with a connected load of 60 kVA, a power factor of 0.8, and a high leg. The NCL is 60 kVA, which is 60,000 volt-amps. The voltage is 208 volts, line to neutral. The power factor is 0.8. To calculate the amps without a high leg, use the formula amps equals 60 kVA, which is 60,000 volt-amps, divided by the quantity 208 volts times 0.8. This results in amps equals 353.3 amps. To calculate the amps with a high leg, use the adjusted formula amps equals 60 kVA, which is 60,000 volt-amps, divided by the quantity 1.73 times 208 volts times 0.8. This results in adjusted amps equals 208. Therefore, the appropriate amperage for the three-phase service panel with a higher leg is 606.6 amps. Sizing a three-phase service panel requires careful consideration of the connected load, demand factors, diversity factors, voltage, and power factor. Understanding and applying the correct formulas ensures accurate amperage calculations, especially when dealing with high leg configurations. Failure to account for these factors can lead to undersized panels, causing overloading and potential safety hazards. The net calculated load, or NCL, is a crucial step in determining the total electrical demand on the service panel. It represents the sum of all connected loads adjusted for demand and diversity factors. Demand factors account for the fact that not all connected loads will operate at their maximum capacity simultaneously. For example, lighting loads may only operate at full brightness during certain times of the day, while motor loads may only operate intermittently. Diversity factors account for the varying usage patterns of different loads. For example, residential appliances such as refrigerators and washing machines have duty cycles, meaning they cycle on and off. This reduces the overall demand on the service panel compared to the sum of their nameplate ratings. The power factor is a measure of how effectively electrical power is being used. A power factor of 1.0 indicates that all the power is being used to perform work, while a power factor less than 1.0 indicates that some of the power is being wasted. Power factor is influenced by inductive loads such as motors and transformers. These loads cause the current to lag behind the voltage, resulting in a low power factor. Utility companies often charge customers with low power factors, as it increases the burden on the electrical grid. Power factor correction can be achieved by adding capacitors to the electrical system, which compensate for the inductive loads and improve the power factor. The presence of a high leg in a three-phase system requires special consideration when sizing the service panel. A high leg, also known as a wild leg or stinger leg, is a conductor that has a higher voltage to ground than the other two conductors. This higher voltage can create safety hazards if not properly accounted for. In a 240 volt delta system with a high leg, two of the phases are 120 volts to neutral, and the third phase, the high leg, is approximately 208 volts to neutral. This requires the use of the adjusted formula to ensure that the service panel is adequately sized to handle the additional current. The selection of the appropriate service panel size is critical for the safe and reliable operation of the electrical system. An undersized panel can overload, leading to overheating, insulation damage, and even fire. An oversized panel, on the other hand, is unnecessarily expensive. The National Electrical Code, or NEC, provides guidelines for sizing service panels and feeders. The NEC specifies minimum ampacity requirements for various types of loads and provides tables for calculating demand factors. Compliance with the NEC is essential to ensure the safety and compliance of the electrical installation. When sizing a three-phase service panel, it's important to consider future expansion. Adding additional loads in the future may require upgrading the service panel to a larger size. Planning for future expansion can save time and money in the long run. It's also important to consider the physical space available for the service panel. Service panels come in various sizes and configurations, and it's important to choose a panel that fits within the available space. Ensure that there is adequate clearance around the service panel for maintenance and repairs. Working with a qualified electrician is recommended for sizing and installing service panels. A qualified electrician has the knowledge and experience to ensure that the installation is safe, code compliant, and meets the specific needs of the application. It can also perform load calculations, select the appropriate panel size, and install the necessary wiring and overcurrent protection devices. The calculations for sizing a three-phase service panel are based on Ohm's law and the power equation. Ohm's law states that voltage equals current times resistance. The power equation states that power equals voltage times current times power factor. These equations can be used to calculate the current draw of various loads and determine the total demand on the service panel. The voltage used in the calculations is typically the line to neutral voltage. This is the voltage between one of the phase conductors and the neutral conductor. In a 208-volt system, the line to neutral voltage is 120 volts. In a 480-volt system, the line to neutral voltage is 277 volts. The power factor is a dimensionless number between 0 and 1. It represents the cosine of the angle between the voltage and current waveforms. A power factor of 1 indicates that the voltage and current are in phase, while a power factor less than 1 indicates that the voltage and current are out of phase. Most electrical equipment has a nameplate that indicates its voltage, current, and power factor. This information can be used to calculate the power consumption of the equipment and determine its contribution to the overall load in the service panel. When calculating the net calculated load, it's important to consider all types of loads, including lighting, receptacles, appliances, motors, and heating and cooling equipment. Each type of load has its own demand factors and diversity factors that must be taken into account. Lighting loads are typically calculated based on the square footage of the building and the type of lighting fixtures used. Receptacle loads are calculated based on the number of receptacles and their intended use. Appliance loads are calculated based on the nameplate ratings of the appliances. Motor loads are calculated based on the horsepower rating of the motors and their duty cycles. Heating and cooling loads are calculated based on the size of the building and the climate. Once the net calculated load has been determined, it can be used to select the appropriate service panel size. Service panels are rated in amps, which represents the maximum amount of current that the panel can safely handle. The service panel should be sized so that its ampacity is greater than or equal to the net calculated load. In addition to the service panel, the feeders that supply power to the panel must also be sized appropriately. Feeders are the conductors that carry power from the utility transformer to the service panel. The feeder ampacity must be greater than or equal to the net calculated load. The size of the feeders is determined by the ampacity of the conductors and their insulation type. The NEC provides tables that list the ampacity of various conductors based on their size and insulation type. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect the service panel and feeders from overload in short-circuit conditions. These devices are designed to trip or blow when the current exceeds a certain threshold, preventing damage to the electrical system. The size of the overcurrent protection devices is determined by the ampacity of the conductors they are protecting. It's important to select overcurrent protection devices that are properly rated for the application. Using undersized overcurrent protection devices can result in nuisance tripping, while using oversized devices can allow excessive current to flow, potentially damaging the electrical system. Proper grounding is also essential for the safe operation of the electrical system. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection devices to trip and clear the fault. The grounding system must be properly installed and maintained to ensure its effectiveness. The NEC provides detailed requirements for grounding electrical systems. Regular maintenance and inspection of the service panel and feeders are important to ensure their continued safe and reliable operation. Service panels should be inspected periodically for signs of corrosion, loose connections, and damaged components. Feeders should be inspected for signs of insulation damage and overheating. Any problems should be corrected promptly to prevent further damage and potential safety hazards. When working with electrical systems, it's important to follow all safety precautions. Always disconnect power before working on electrical equipment. Use appropriate personal protective equipment, such as gloves and safety glasses. Never work on electrical equipment when wet or damp. If you are not comfortable working with electrical systems, it's best to hire a qualified electrician. Sizing a three-phase service panel is a complex task that requires careful consideration of various factors. By following the steps outlined in this guide and consulting with a qualified electrician, you can ensure that your electrical system is safe, reliable, and code compliant.